Log on, tune in, find out. Another good idea from Cambridge.
I'm particularly pleased to introduce our last speaker, Peter Zemrock, because I think he's the only speaker today who's a co-author of mine, even though there are other such people in the room. He was, I can't remember at the time, but he now works at Shell, and he's going to tell us about experimental design challenges in fuel and lubricant research and development. Over to you.
Okay, thank you very much, Rosemary. Thank you to David also for inviting me today. I work for the Statistics and Chemometrics group of Shell Global Solutions. So I'll start with a few words as to who we are, and I'll then move on quickly to our colleagues in fuels and lubricants and tell you a little about what they measure, how they do it, what the experimental design challenges are in what they do, and I'll finish with a fuel blending case study. So we're a team of 15 statisticians and chemometricians based at 3 sites, Chester, Amsterdam and Houston, and we provide statistical consultancy to most parts of the Shell business, particularly product development, but also manufacturing, that's refining and chemicals, the upstream, which is exploration and production, and also central office functions such as retail, finance and trading. So, fuel and lubricant development. What do we measure? Well, starting first of all with fuels, obviously things like octane number, which tells you how many stars your petrol have. Exhaust emissions, very important. Fuel consumption, volatility. Hot and cold weather drivability. Does your car start well? Does your car knock? Power and acceleration, and so on. And for lubricants, we measure physical properties like viscosity. Very important to measure engine wear and cleanliness using a particular lubricants. Lubricants also have an effect on fuel consumption. Very important is durability. How long will an oil last before you have to do an oil change? How well does the oil perform in very cold conditions? Will it still pump around the engine? How do we measure it? Well, for come on. Maybe I should stop playing with the this little thing. Yeah, okay. Simple physical properties like volatility or viscosity or pumpability, you can measure these in laboratory tests. But soon you start having to use test engines, so octane number is measured in a single cylinder engine. Engine wear and cleanliness, you can do it in a test engine, very expensive tests, and likewise lubricant durability. But soon people ask you to sort of demonstrate how fuels and lubricants are going to perform in a car or a heavy duty vehicle. And that brings us on to chassis dynamometer tests and field trials, which I'll talk about in a little more detail. So a chassis dynamometer it's a sealed unit where a car is mounted on a rolling road and it's sort of clamped on it. And then you drive the car over these rollers using standard cycles, and this would be done by an expert driver, or in some applications even a robot. It's in a sealed unit, so you can control the ambient temperature. And typically you would collect the exhaust gas in bags, so there's a little tube attached to the exhaust pipe, and you would measure things like unburnt hydrocarbons, carbon monoxide and dioxide, NOx, etc., and particulates. And interestingly, you can calculate fuel consumption from gaseous emissions, and that's one of the more accurate measures of actually measuring fuel consumption using the carbon balance method. So what challenges do chassis dynamometer tests pose for us when we're doing an experimental design? Well, first of all, engines do drift over time. So if you test an engine for long periods, you're going to get changes in its mechanical condition. You might get subtle changes in driver behaviour. We can't control ambient pressure and humidity. We can control temperature, but not pressure and humidity. And modern engine management systems, which Justin was talking about this morning, can adapt to changes in fuel properties, and so it can be quite hard to correlate performance to fuel properties if the engine management system is changing. And fairly obviously you have limited scope for randomisation, because obviously you can't change the car after every single test. And even changing the fuel or the lubricant takes time, because the previous fuel or lubricant needs to be thoroughly flushed out, because traces of the previous fuel or lubricant, and more particularly the additive packages, can absorb onto the engine, and this gives you a carryover effect. So that is not a good design. So it's important that when you design a test program that you do use true repeats. So if we look at these two tests, these are two tests on the same fuel conducted back to back, and these are just not independent, and all you can do really is work with the average of those two results. But if you consider this test and this test, these are true repeats because you have tested it into a different fuel in the interim. So in an ideal world, you just use a standard randomised block design, but of course you do need thorough flushing between tests. Another design we occasionally use is a sort of bracketed design where you comparing a test fuel with a reference fuel, and all you do is just alternate the two fuels, and you then look at the difference between the result on the test fuel and the two reference results either side of it, and so you calculate these deltas, and then you just work with the average of these deltas. And this is quite good at reducing the effects of non-linear trends, and it extends very easily to situations where you're comparing two or more test fuels against a single reference. Okay, so chassis dynamometers are fine to a certain extent, but sometimes you actually have to test fuels and lubricants in cars out on the road, and this leads us to field trials. And the reason you might want to do a field trial might be to support a marketing claim perhaps, or perhaps to sell a product to a fleet operator. Now the simplest and best form of field trial is really to do some controlled testing. So typically you might select sets of 4 vehicles of various models, and you would simply run 2 of them on fuel A and 2 on fuel B, and you'd run the vehicles a short time apart, driven by specially trained drivers, so they experience the same traffic problems. But sometimes, you're trying to demonstrate something to a particular operator, and then you are forced to do fleet tests. And an ideal fleet test will have a captive fleet of identical vehicles which perform similar duties repetitively. So the best sorts of fleets are things like supermarket delivery vans, buses, trains, particularly merry-go-round trains going from coal mines to refineries, taxis, monster mining trucks in open cast mining. And ideally, you want to sort of run half on fuel A and half on fuel B. But there are problems. Fuel consumption varies with time, and it varies with season, sometimes dramatically so. Vehicles obviously get older, buses are subject to roadworks, ground conditions can change. You can get changes in topography. In open cast mining, obviously, the holes get bigger. On the railways, we get leaves on the line at this time of year and passenger loadings change. So all sorts of things can happen. So the basic design, we need to split the fleets, obviously, into a control group and a test group. The idea is a test group will receive the test fuel. But we also need to have a baseline period and a trial period. And in the baseline period, both groups will run on the reference fuel. And the idea is just to check that there's no systematic difference between the two groups. I mean, we try to balance them as best we can using historic data, but you know, sometimes there is a difference, and it can be big enough to swamp the fuel consumption benefit you're using for. And then the control group, it's like a placebo. So the control group just stays on the reference fuel in the trial period, and it tells us what would have happened if we hadn't changed fuel. So it protects against systematic changes over time due to weather, road conditions and so on. And then the benefit is simply the difference between the two periods in the test group minus the difference in the two periods in the control group. But field trials do pose a lot of logistical challenges. First and foremost, these are commercial fleets, and so the trial must not interfere with its day-to-day operation. And secondly, there's also an expense. Nearly always you're going to actually have to install a second fuel tank for the test fuel. And then you might have to sort of put special sensors or nozzles just to make sure that you put the right fuel in the right vehicle. And then I spoke about the carbon balance method for measuring fuel consumption. In a field trial, I mean, you're basically relying on the operator actually filling the tank to the brim. So you have to measure it and record it as accurately as you can. Ideally, you need an automated system for recording the date and time, the vehicle number, and how much fuel has been added. You also need an accurate method of recording distance travelled or the work done between fills. Again, ideally, you want this to be automated. For example, the techniques based on GPS. Inevitably, you're going to lose segments of data due to IT problems. It happens every single time. And you're likely to lose vehicles due to mechanical failures, engine changes, in the case of buses, transfers to other depots, accidents. I mean, we had one fuel tank struck by lightning. I mean, it's unbelievable what can happen. So your fleets need to be large to build in robustness. And from experience, typically the baseline and the trial periods need to be about 3 months long. Okay, let's move on to a slightly different subject, which is the design of fuel matrices. Many test programs attempt to relate a measurement such as volatility, starting performance, acceleration, emissions to fuel properties. Now it sounds easy, but it isn't, because fuel properties can be various things. There can be chemicals such as the percentage of aromatics, olefins, ethanol and so on in the fuel. They can be physical, so parameters associated with the distillation curve, vapor pressure. And there can be performance related, octane number as a performance parameter. And this makes it very difficult to actually blend fuels to match a predetermined design matrix, as you can't actually change the chemistry without changing the physics and without changing the performance of the fuel. So we're going to look at a little case study now, and this concerns mixtures of gasoline and ethanol. Ethanol is a biofuel. We're particularly interested in these sorts of mixtures because our friends in the European Commission have mandated higher concentrations of biofuels in future gasolines. Let's just begin by looking at the black line. So this is a typical hydrocarbon base fuel, and this is its distillation curve. So it represents the percent of fuel which is evaporated at different temperatures. When you start to add ethanol, the distillation curve starts to become quite flat, and the more ethanol you add, the flatter it becomes. And this is due to the formation of azeotropes, which are sort of constant boiling mixtures. Ethanol, I think, boils at 78 degrees, so it's a particular problem in this sort of 70-degree area. Let's move that out of the way. One too far. A key parameter of interest is E70. E70 is the percent of fuel which has evaporated at 70 degrees C. So for the base fuel, if we follow the 70-degree line, we see that the E70 is about 36%. If we add 10% ethanol and look at the red line, we see that its E70 is about 56%. And this has consequences, because if you add ethanol, you can take a fuel off specification. A typical limit for E70 in the European fuel specifications is 48 to 50% maximum, depending on the season. So there is an interest in producing models for the E70 and E100 of gasoline ethanol blends. And so a project was sponsored by the European Commission and conducted by Concarwe, who I'm a subcontractor for, and Shell. And it was to model the distillation properties of blends as a function of the concentration of ethanol and the properties of the base fuel it is blended into. So we have to design a base fuel matrix, in essence. And the key properties of interest and their ranges of interest are these. So we've got the aromatics olefins, these are two ethers, DVPE is vapor pressure, and of course it's going to depend on the E70 and the E100 of the base fuel. The ethanol range of interest is 0 to 25%. We have a number of constraints. The first one is that we only really want to use one of the two oxygenates in any base fuel blend, because in practice you're never going to use the two together. To reflect the market, we decided that a good proportion of the base fuels had to be oxygen at 3. And there's a sort of constraint on E100 and E70 in that in most sensible base fuels, the percentage of fuel evaporating between 70 and 100 degrees is going to be somewhere between 15 and 35%. Actually, that's a reference to the final report on this work and the contract. So the way we did it was this. We began by selecting 49 base fuels based on a 1/343rd replicate of a 7/5 design. We designed it using our in-house key finder program, but you can also get it using a Hyper-Greek or Latin square. And we used the first 3 factors A, B and C to determine the levels of aromatics olefins and vapor pressure in the usual way. Then we used factor D to simultaneously set the levels of E70 and E100. So this quadrilateral is the feasible region for E70 and E100. E100 obviously has to be higher. And we've just made an evenly spaced selection in that sort of region. And likewise, we used factor E to simultaneously set the levels of MTBE and ETBE. So if E is 0, then we didn't put either ether in. If the factor was 4, we put 11% ETBE in. If it was 5, 22%, and ditto for MTBE. Now, we were trying to get an evenly sort of spaced design using the fractional replica. But one of the come on. One of the come on. Right. One of the features of hybrid Greco-Latin squares is actually you get very few corner or edge points, and that means you're not fully spanning the design region. To get to a sort of edge or a corner, you have to have lots of 1s and 7s in a particular row of the design matrix, and you tend to find that most of them have a number of 2s, 3s, 4s, 5s and 6s, so you're not quite at the corners or edges. So what we did is we added 11 further fuels, and we selected these from a set of candidates to minimise the usual de-optimality criteria, and we did it using the Mitchell algorithm coded up in SAS. And we ended up with 60 fuels which had a correlation matrix looking like this. You'll see that nearly all the correlations are pretty low, apart of course from E70 and E100, which are obviously always going to be highly correlated, and MTBE and ETBE will always be negatively correlated because you're never putting the two ethers in together. So those 60 fuels were a challenge for our blenders, who had to work only with standard refinery components, but they did very well in blending the fuels. So these are the actual measured values, and it's a simple matrix plot of some of the parameters, the physical ones on this side and the chemical ones on that side. And you'll see that most of these are fairly orthogonal, and we've plotted the 11 extra points in red, and you'll see that all of these are at the edges. So our blenders did very well, apart from this top corner. You just cannot make a high aromatic high E70 fuel, and we're not going to do it artificially because what's the point? Finally, we just had to arrange the test order. E70 is not a very repeatable measure, so we did the distillations in triplicate for each base fuel with 6 concentrations of ethanol, when we used a random blocks design with a different randomization obviously for each base fuel. And we completed the 18 tests on one base fuel before starting on the next. Why did we do it? We did that because our prime concern is to get an accurate measurement of the delta, which is the difference between the E70 of a blend and the E70 of a base fuel. So it's good practice to actually do these two measurements close together. And obviously we tested the base fuels themselves in a randomised order. Okay, so that's more or less it. Just a few final thoughts. Obviously, I hope I've shown that fuel and lubricant R&D poses quite a lot of design challenges to the statistician. Tests are constrained by cost, particularly engine tests and fleet trials. They're constrained by logistics, particularly fleet trials. We have to worry about carryover effects when we're doing CD tests and changing fuels and lubricants, and we have to work within the laws of nature for things like distillation curves. Field trials in particular are prone to the unexpected, and even when you conduct them perfectly, the benefits are often hard to isolate due to the many sources of variation. So the subsequent data analysis poses just as many challenges, but hopefully you can ameliorate these by good experimental design. Okay.
Questions?
Right. Hi. Do you do a similar design when you do the octane blending? I mean, like the
Yeah,
fuel
we
comes
did
out
some
of-
work about 25 years ago for the octane blending, and actually I remember doing it using cluster analysis because we did actually have a huge library of base fuels we could work with, and so we used cluster analysis to sort of arrange the candidate points into clusters, and then we just took the middle point from each cluster, and that gave us an evenly spaced design which worked quite well. So there's a paper in Technometrics on that about 1985. So that was specifically for, it was for blends of gasoline and ethanol.
So do you do, say, refinery? I'm like, in the refinery, at some point when you sell your product, okay, depending on how you mix the different refinery streams, you get some octane numbers. And it's not always trivial to decide how much to take from each pot. And there's a cost associated to each pot. And that depends very much on the chemical and therefore non-linear interaction between the different components.
Absolutely.
So the question is, are you using statistical techniques to associate a specific mixture with such non-linear responses as, for example, the octane rating of a resulting mixture?
I mean, obviously, work on that sort of thing has been done over the years, and the refineries do have their own blending models which are based on obviously empirical data. We haven't done any recently, and there's an element of commercial confidentiality about the models we use, I'm afraid, so I can't really say too much. I do apologise. But I mean, obviously, if you were trying to design such an experiment, you would have, you'd be using maybe constrained mixture designs, a whole variety of things you could do. And obviously then you have optimization processes at the plant itself, you know, to make sure you don't give away too much quality.
Going back to your first discussion of the field trials, it's like I can see there's all sorts of practical problems associated with that. It's quite challenging, I'm sure. I'm wondering if possibly something like balanced incomplete block designs might be useful in terms of comparing lots of alternatives with relatively small numbers of vehicles.
For the field trial? Field trial, you would typically be really trying to discern quite a small fuel consumption benefit, and you are doing this with the background of a high level of vehicle-to-vehicle variability. So you are not in the fractional replicate design arena. You're in the arena where you're having to do lots of repeat replicates.
It's mixed design. It's mixed model. You have some random variability and some fixed changes. Yeah. So balancing the block, box and Tiao analysis would allow you to recover these block information.
It really is. It's at a different level. It is. You know. I mean, you only have in a typical field trial. You have two fuels, and you're just trying to compare the two fuels, and you need to allocate a large number of vehicles to each of them. There really isn't the scope to do anything more than a simple design where you have one factor with two levels. You haven't got the statistical power to do anything more subtle. You do that, if you're going to do that, you're going to do it in a lab on a test engine, not in the field. I mean, the field test is the final proving stage. You know, you have different levels. I mean, obviously, you begin your research with lab tests and you move on to test engines. Test engines are expensive. I mean, if you're working particularly with lubricants, one test on a test engine can cost you tens of thousands of pounds, because you're driving that engine to destruction almost to see what damage is going to happen when you use lubricant for an extended period under very severe conditions. So really, you have to get your research bit right before you ever get to a field trial. And the field trial is about selling the product to the customer. It's not a research tool, it's a proving
I'm
tool.
thinking more about the most effective way of removing the random effects, so that you can find the smallest differences in the fixed effects most efficiently, and that's what they would be good for.
Obviously, you want to do it in the same vehicle if you possibly could, but I mean, then you have the issue of time effects. So, when you have a number of vehicles, in a fleet, I mean, say you've got a number of buses, I mean, you've got to be doing different routes on different days. We're going to pick up different numbers of people. They use different amounts of fuel on a Sunday, and you've got to not interfere with, the operations of that particular bus company. You can't change the fuel frequently because you've got to flush out all the old fuel, so it's not realistic to have multiple changes. So, I mean, the logistics are totally against doing anything more sophisticated out in the field. You've got to do it in the lab. And balanced incomplete blocks. I mean, we do use them for certain sorts of in-house testing, yeah.
They might be useful, but they actually originally, one of the conceptions originally was to avoid problems with one of the main reasons for using them originally was the idea of avoiding those logistical problems when you can't put incomplete blocks, for instance, because as you say, you have limited number of vehicles, or you can't always test every factor combination for each set.
Yeah, but you're talking about controlled testing now, not field trials. So you're talking.
No, I'm talking about field trials.
The field trials with an actual fleet of buses or monster trucks. So
the type of vehicle could be one factor, for instance. The route could be another factor, but you don't have to do every combination of all, and you can recover the.
It's all coming down to signal to noise at the end of the day.
So you can remove they allow you to remove the random effect and get a more precise estimate of the main effect. You do them correctly. Box and Tiao is a good.
Yeah, I know the theory of it. I think in terms of the practicalities, there's just no way we're doing tests in an open cast mine, say. I mean, to try sort of get a set of guys working in a wild environment to actually drive their trucks according to a sort of design which we had set out and do all the things involved with, we can't tell the trucks where to go.
But you could with the buses. So to take your point, you could have bus route going A and bus going route B.
Yeah, that's one factor.
And what would you change?
The fuel. So you've got the fuel and the bus.
Yeah, but you've got to then flush out all the old fuel. So I mean, there's a fuel.
Can I interrupt?
Yeah.
Bus routes A and B are 2 blocks,
Yeah.
and you use both your fuels on some buses on route A, and you use both your fuels on some buses on route B.
Yeah. Yeah.
Or there could be other
Yeah.
things in other situations
Yeah.
where you can see some differences.
Yeah.
Allocate both fuels
Yeah.
to both.
Oh, indeed. Yeah.
And then you can take out that
Extract the
difference from
random
your
effects.
aerodynamics.
But I mean, obviously, one of the difficulties with buses is obviously the fueling. So you have to have such a good relationship with the bus company, and you have to install a second fuel tank, and then you have to be very, very careful that you have a good mechanism in place to make sure the right fuel goes into the right bus. But it kind of becomes...
The more complicated the design, the more likely it is to go wrong.
Absolutely.
But on the other hand, you might get more out of it. I think this is a fascinating discussion, but given the time, I think we should stop now. And first of all, please join me in thanking all of our speakers.